So we have finished our discussions on static friction and kinetic friction. There's another type of friction which is the rolling friction. So that is the friction when you roll something on a surface, right? And in our experience, the rolling friction is much smaller than the kinetic friction. Okay, if you slide the same wheel, if you have a wheel, you slide it against the surface, and you can feel the resistance is definitely larger than rolling on the surface. Okay, another example, real life example, is that when you're driving your car in normal conditions, the wheels, the tires are rolling, right? And then, but when you hit the brakes really hard, and then the tires slide against the road surface, that's the kinetic friction. Okay, so you can definitely feel when you do that the resistance from the road is really it's much larger than the resistance from the road on the tires or when it's rolling. Okay, so the theory for rolling friction that we also have a empirical theory for rolling friction. So it's very much like the kinetic friction. So it's almost a constant. Okay, and then that's proportional to normal force, and then the coefficient we call it coefficient of rolling friction. So the behavior of rolling friction is very similar to kinetic friction. So that's why we're not going to really go into details here, because the theory is the same. The behavior of this rolling friction is the same as mu k. But what we know is that in our experience, right, rolling friction, the coefficient of rolling friction is going to be much smaller than the kinetic coefficient of kinetic friction. And if you take a look at the table on the last slide, I listed the 3 different coefficients of friction for some given surfaces, and you can definitely see this mu r, this rolling friction, it's much smaller than mu k, and mu k is also smaller than mu s, and that is why, again, that agrees with our experience, right? Sliding something, okay, moving something on a surface is definitely easier than start this thing in motion. And if you have a wheel, then rolling it is definitely easier than sliding it against the surface. Okay, so that's the third friction, the rolling friction. So we have finished our discussions on friction forces. Now we're going to move on to a new topic. So that's the next PowerPoint. Circular motion. Okay, so circular motion is not that intuitive as straight line motion. That's why we want to study that in a little bit more detail. Okay, but we're going to still use the same laws of motion, Newton's laws, when we study circular motion. That's the beauty of physics. Okay, if you look around you, you do see complexity. You see complicated, nature's really complicated, but you also see patterns. You see orders. You don't really see chaos. Okay, so what physicists do is that to find the orders, okay, in very complicated nature, okay, and then once you found the fundamental laws, you can always use the fundamental laws to make predictions in different scenarios. Okay, so circular motion, the laws are still the same. We're going to still use Newton's laws to study circular motion, but because it's different than straight line motion, we want to spend some time discussing that. Okay. So the first question I want to ask you is this. Take a look at the question on the first slide. What is the direction of the force in order to keep an object in circular motion? So this is not intuitive to a lot of people. Okay, like the first time I learned circular motion, this was really weird to me. Okay, so if you think about it, right? Think about any circular motion in your life. Okay, in your life. Okay, what is the force in order to keep the object in circular motion? Okay, the answer is a force toward the center. Okay, again, this is not intuitive at all. Okay, because usually people would think that the force, if something's moving, the force is always in the direction of the motion, right? That's intuitive to us, right? If I want to move something in a certain direction, I'm going to apply a force in that direction. But that's the simplest case, right? We have learned a motion where the force is not in the same direction of the motion. Which motion is that? We learned that in this class. Projectile motion. If you think about projectile motion, right, you throw something, the direction of the motion actually is changing all the time, right? If you throw something even horizontally, you see it moves this way. So the direction of the motion is actually changing all the time, right? At this point, it's going to be in that direction, and then tangent. What is the direction of the force on it? The forces are not in this direction, right? The force is gravity. So the force on it actually is always down and is always constant. Okay, so you see the difference, and that is why it's not moving in a straight line, because the force and the velocity are not in the same direction, so it's not going to be a straight line motion. Okay, so that's why we should always use laws discovered, okay, theories discovered in nature instead of our intuition, right, to study things. If you only trust your intuition, okay, you're going to be very limited, okay, on the things you can make predictions. Okay, so again, as I said, think about all these circular motion you see around you. You can always find a force toward the center on this object moving in a circle. Always. Okay, there's no exception. Okay, think about hammer throwing. Right, think about hammer throwing. Okay, the person is swinging this hammer using a string, okay, and he's always pulling the string toward himself, right? So in this case, there's always a force on this hammer toward the center of the circular motion. In some cases, there's also a force tangent to the circle, okay? In some cases, when the velocity, the speed of this object in circular motion changes, so in that case, there will be a force tangent to the circle. But that is not the force, okay, in order to keep this object in circular motion. If you want to keep this object in circular motion, there must be a force toward the center, okay? This force tangent to the circle is not necessary, okay? It can change the speed of this, this object in this circular motion. And we're going to actually study that in the angular motion chapter, okay? So that force can be on the object, but it's not necessary in order to keep it in circular motion. In order to keep it in circular motion, it's the force always toward the center. And as I said, you can think about all the circular motions right, you see in your real life, okay? And you can always find a force. Okay, and that force can come from like different things. Right? Okay, you can always find a force toward the center. Okay, so that force we call it a centrifugal force. Centrifugal, this word means center seeking. Okay, so because there's always a force toward the center, so there's always a acceleration toward the center, and then this can be proved. Okay, the centrifugal acceleration has a magnitude and the direction is always towards center. So as I said, you don't trust your intuition always. In this case, this is very non-intuitive. What is the direction of this force on the circular motion? But if you use the definition of acceleration, okay, which is the changing velocity divided by changing time, okay, and then you pick a very small piece of this circular motion, you apply that theory, okay, you can find that if you do changing velocity divided by changing time, so the changing velocity, you cannot just subtract two numbers, right? So in this case, you would do this. This is the VI, okay, and this is the VF. How do you subtract these two vectors? You can do that pictorially, right? So you're going to do, if you want to do VF minus VI, so you're actually going to do VF in that direction, and then you're going to, excuse me, you're going to actually draw a VI in this direction, right? A negative VI. So first you're going to make a negative VI, which is in this direction. So I'm going to show you how to derive this actually. And then if you, then you're going to, this equals VF plus negative VI, right? And then how do you add these two vectors? You're going to draw this second vector starting from the tip of this. So this is VF, this is negative VI. Now you're going to connect these 2 points. This is delta V, right? So this is how you subtract these 2 vectors. So it's not intuitive at all, right? You have to use the vectors and the definition of the subtraction, addition of vectors to find this vector. You see that you find a vector, whatever these 2 are called, right? This is A, this is B, then this is the sum of them, okay? This delta V is toward the center. And then if you do delta V divided by delta T, you will get an acceleration toward the center. Okay, you will get an acceleration toward the center. Okay, so that's how you prove it. Okay, so we're not going to really show the details. Okay, we're just going to use the conclusion. You can prove that, okay, using the definition of acceleration, and then you make the time, take the limit till time goes to almost 0. Okay, then you can find the acceleration is always toward the center. Always toward the center, okay? And the magnitude is always going to be this, okay? So the centrifugal acceleration, okay? So this is not intuitive at all, right? You can prove that, again, using this definition. We're not going to prove it here, so we're just going to use the conclusion, okay? So at the end, you will find that at any point of the circular motion, the centrifugal acceleration, the acceleration toward the center, always has this magnitude, v squared over r at that certain point. Okay, so it's very interesting. Even this acceleration is not going to be a constant if the speed changes, right? Okay, so I think you see that things that can get like, very complicated in nature, but the theory, the laws are still the same, right? The definition of acceleration is still the same. But you should, when you work with a circular motion, then the vectors are going to get a little bit more complicated. But anyway, we're not going to really worry about the proof in this class, because this is an intro-level class. We don't want to make it too complicated. We're just going to go ahead and use this conclusion. So for every circular motion, there's always a force toward the center to keep this object moving in circular motion, and the magnitude of this acceleration we call centrifugal acceleration. It's always v squared over r. So, and then if you know the centrifugal acceleration toward the center is this value, then you can also calculate the force toward the center, right? Which we call centrifugal force. Okay, so that's the centrifugal force equation. Okay, so this force is also toward the center of the circle. And of course, it's going to be perpendicular to the direction of the velocity. If the velocity at any point is going to be tangent at the tangent to the same circle, right? Okay, so these are the 2 very useful conclusions. Okay. So so again, a few points I want to make here. Centrifugal force is not a new type of force. Okay. So some people, they may have this impression that, oh, now we have learned another force other than gravity, normal force, and friction force. Okay, so when I draw a Fibber diagram, I would draw gravity, normal force, friction force, and then I'm going to draw a centrifugal force on this Fibber diagram. No, you don't. Okay, what we learn is this. Anything moving in a circular motion, there must be a net force toward the center to keep it moving in this circular motion, okay? And then this net force, remember this is a net force, so it doesn't have to be only one force, and actually we're going to see some examples, okay, where several forces are the centrifugal force. So the net force has a strength like this value. But what is this centrifugal force? Okay, what is the centrifugal force in this circular motion? You must identify that force, okay? So different forces can be centrifugal force, and we're going to see a lot of examples. Tension can be centrifugal force, right? Friction can be centrifugal force, gravity, or electric forces we're going to study in Physics 2, if you're going to take Physics 2, can also be centrifugal force. Okay, so when you draw a fiber diagram, you still draw all the forces you know. Okay, you normally draw gravity, normal force, friction force, tension, okay, things like that. Then you're going to use the motion of this object to find out which force is the centrifugal force in this case. Okay, you don't need to draw another force called centrifugal force in the fiber diagram because you're going to double count. You don't do that. Okay, centrifugal force is not a new type of force, so it's just a name we assign for this net force towards center in a circular motion because it's very special. It's different than straight line motion. That is why we made this name. So think about this. I can give you an analogy. I can make a word. I can say stopping force. Okay, a stopping force is needed to stop an object, right? I can make this phrase, but I'm not making a new force because the stopping force can be any force, right? I'm just saying that, okay, anything stops needs a force to stop. So I can find out the stopping force in any situation or something stops, right? I'm not making a new force. For example, if something's moving on a surface, the friction can stop it. So I would say, in this case, the friction is the stopping force, right? Or if something runs into a wall, and the normal force from the wall can stop this object, so I would say, oh, in this case, the normal force from the wall is the stopping force. Okay, so any force can be stopping force. If I make this phrase, okay, to just describe some sort of force that stops an object, okay, and I want to just use this phrase. So I'm not making a new type of force. When I draw a fiber diagram for anything stops, right, I would draw gravity, normal force, friction. I don't need to draw a force called stopping force on this object. Right? Okay, so that's what it means. Again, we're going to see some examples so you know what I mean. Okay, it's always easier to understand a theory in a real example. So that is what we'll do in this lecture. But first of all, let's take a look at some real world examples. Okay, if you know the structure of an atom, okay, I'm sure that pretty much like everyone knows that. Okay, if you are in college. We know that the structure of an atom is a nucleus at the center. Okay, take a look at the image on the next slide, slide 4. A nucleus has protons and neutrons, right? It's made of protons and neutrons. And neutrons, they are neutral, they don't have any electric charge. Protons, they carry positive charge. And if you're going to take physics 2, you're going to study electric forces in detail in physics 2. And electrons, they carry negative charge, okay? And there are electrons orbiting the nucleus all the time. Okay, that's the structure of an atom. And then you can see that if you draw it out, the nucleus at the center, right, there's protons and the neutrons, and then the electrons orbiting the nucleus. And then if you know that the like charges repel, unlike charges attract, the protons are always going to attract the electrons. So see that the electrons, when they are orbiting the nucleus, they always feel an attractive force toward the nucleus. So that's the centrifugal force that keeps these electrons orbiting the nucleus. In this case, the electric force is the centrifugal force. Right? Centrifugal force can be any force, can come from any agent. You have to identify which force is the centrifugal force in different cases. Now think about the solar system, our solar system, right? Every planet orbits the sun, and then they move in an elliptical, okay, circuit, orbit, okay, not perfect circle. But what is the force that keeps them orbiting the sun? That's gravitational force, right? We're actually going to study gravitational force in detail at the end of this class. And a gravitational force is always attractive. So there's always an attractive force from the sun on, say, the earth toward the sun, right? So when the sun is orbiting the earth is orbiting the sun, okay? There's always a force toward the sun. So that's the centrifugal force for the earth to move in a circular motion, almost a circular motion, not perfect circle. In this case, gravitational force is the centrifugal force, okay? Now take a look at the next slide. This is an interesting one. Say if you're driving a car, right? If you're driving a car, you're making a turn. You're making a turn, you're not going straight, right? You're driving in an arc, but that's part of a circle. So in this case, your car is still moving in a circular motion. It doesn't complete the circle, but it's still in a circular motion. In this case, which force is the centrifugal force? There must be a force that keeps the car in this circular motion. Think about it. Which force is the centrifugal force? Friction force, right? And the friction force from the ground is the force on this car always toward the center, okay? Because remember, the friction force can be in any direction, right? If you, for the same surface, if I move this thing that way, the friction is in this way. If I move this thing that way, the friction is this way. If I move this thing that way, friction is that way. So friction force, as long as it's parallel to the surface, right? So it can be in any direction, the friction force, depending on the motion and the attempted motion. So in this case, if the car is moving in a circle, in a circular motion, let's draw a bird view. So it's making a turn, so it's moving this way, okay? Now there must be a friction force always toward the center. So that's a theory, right? This is not intuitive at all, but you don't always trust your intuition. You don't, okay? So there's always a friction force toward the center in order to keep the car, okay, making this turn. Now this is a friction force because that's the only force from the ground on the car and then can be in this direction. The ground also has normal force on the car, but it's in this direction, right? If this is a bird view, the gravity is in that direction and then the normal force is in this direction. So the normal force cannot be in this direction. So the only force that comes off the ground that can be in this centrifugal direction, that's the friction force. Because friction force can be in any direction on the surface as long as it's parallel to the surface. Another question I want to ask you is this. Think about it. So we have learned 3 types of friction. This friction, is it static, kinetic, or rolling? Which friction is this? Think about it. What is your answer? The answer is static friction, okay? So it's not kinetic, it's not a rolling. First of all, it's not sliding on this road, right? So it's definitely not kinetic. And some people may think it's rolling, but the rolling friction, it's in the direction of the motion, right? Remember, at any point, this is the direction of the V at this point, right? So the rolling friction actually is going to be in this direction. Okay, so that's the rolling friction. Rolling friction is always opposite to the rolling motion, right? At this point, this is the direction of the V, right? Tangent. So the rolling friction is going to be opposite to the rolling motion. So at any point, the rolling frictions are going to be always opposite to the rolling motion, and this direction is perpendicular to the velocity, right? So the car is not moving in this direction. The car is not moving in that direction. What friction is that? That's actually static friction. So it's very interesting. You see that when the car is making a turn, okay, there are actually 2 types of friction forces on the tires. One is rolling friction, and the other one is the static friction toward the center to keep this car in this circular motion. Okay, so it's very interesting. The theories are always the same, but things can get complicated, right? Things can get complicated in real life. That's when we use the laws and the theories. We don't always trust our intuition because we don't really see these forces. We don't see any forces, right? We don't see any arrows in our life, right? We can feel forces. Like I feel gravity is down on me every day, all the time. right? But I don't see the force. I don't see a number on me, right? Mass times 9.8. No, okay? So that's when you use laws and theories, okay, discovered in nature to study anything that's complicated, okay? So, and then that explains why it's dangerous to make sharp turns on icy roads. When the road gets icy, right, so the static friction coefficient is going to get smaller. So the car cannot get a very large static friction from the road, right? Remember, the static friction force has a maximum value. Okay, if you want the car to finish this turn, right, in a circular motion, in the arc, you want a certain static friction from the road, and the static friction force can vary, okay? So that's why you can make this turn at different velocities. You see, everything is consistent, because the static friction is not going to be a constant. But this static friction force can only go to a certain limit, right? And then when the road gets very icy, this coefficient mu s is going to become very small. So that means the road can only provide the car a very, very small static friction force. So it may not be able to, make a sharp turn, okay? And then think about it, what do you usually do if you make a very sharp turn on icy roads? Or, when you make a turn, you always slow down, right? Why do you slow down? Because now you can see it's physics. If you slow down, velocity gets smaller, the centrifugal force needed to keep this car in this circular motion is going to be small. So you make this centrifugal force needed smaller, so the road can still provide enough centrifugal force for this car to make this turn, okay? All right, see that physics is everywhere, right? Okay, so that's all conceptual and real-life examples. Now we're going to study the simplest circular motion in detail. We're going to, again, use the theories we learned to practice them, okay? So the simplest circular motion is the uniform circular motion. So that's when an object moving at a constant speed around a circle. So that's going to be in a perfect circle, okay? You shouldn't say the object moves at a constant velocity, strictly speaking, because the velocity has, we usually call velocity the vector. The velocity has magnitude and direction. So the velocity actually changes all the time, but the value can stay a constant. The value can stay a constant, right? So you can do that, right? For example, if I want to swing this guy, right? I can sort of do that using a constant speed when I swing in a circle, right? Even though the velocity is always changing, the direction always changing, I can make sure that it moves in a circle at almost a constant velocity. So that is the simplest circular motion, right? So, and then the speed is a constant in this circular motion. It will move in a perfect circle. So, but the direction of the velocity is changing all the time, right? The velocity, the direction of the velocity is always changing. And then the centrifugal acceleration of force, they are always toward the center. So the centrifugal force and acceleration are always perpendicular to the velocity. Right? Take a look at the arrows on this slide 6. Because you have one vector always toward the center, one vector always tangent to a circle, then you always have them perpendicular, right? So the centrifugal acceleration and force, they're always at any point, right? If it's moving in a perfect circle, it's always, this is centrifugal acceleration and force, and this is the velocity. At any point, it's going to be perpendicular. Okay. So if this if it's moving at a constant speed, so it's always going to finish a circle at the same amount of time, right? In the same amount of time. So then we can define a thing. So the the time for it to complete the one circle is going to be a constant. So a constant, usually we will give it a name, okay, because it's very useful, okay. So in this case, we call this time, the time for one complete revolution, we give it a name, we call it period, right? And then we usually use this symbol big T, okay, for the period. It's still a time, but it's a very special time. It's a time for anything in a uniform circular motion to complete one revolution, one full circle. And then we can actually convert, we can connect this period to the speed of this circular motion, okay? How do you connect them? So think about that. If I want to calculate speed in this circular motion or any motion, right, I would just do distance over time. If it's in x direction, I would just say changing x divided by changing time. This is the definition, so this is always true. Always true. That's why we call them a definition, right? Now, if I apply this definition in a uniform circular motion, so I can pick like a very special time, the period, because it's always going to complete the full circle in a period, okay? And if I pick this as the time, so I should put the distance it travels for one period at the top, so to calculate the speed, right? And the speed is a constant, so I should always get the same number in a circular motion, uniform circular motion. And what is the distance the object is going to travel in one full revolution? That's just the circumference of this circle. And the circumference of the circle is 2 pi r. So see that this is a very nice conclusion from the definition of velocity, and this is a very useful conclusion in uniform circular motion, okay? And this, again, this is not something you to memorize. This is a conclusion. This is not a new theory. This is a very special conclusion of this definition of speed, right? If you understand the definition of speed, you can write this equation yourself, okay? So that's what we're doing. We're not memorizing these shortcuts. Sometimes we will have some useful, okay, conclusions and shortcuts we use in problem, but you don't really need to memorize these equations, okay? You're going to try very hard. I need to memorize this and that. If you understand them, okay, you can even show them on a test, and this is only going to take you, right? This is going to take you like 5 seconds if you understand how we got it, right? This is just a conclusion from the definition of speed, all right? Okay. Now let's take a look at an example. As I said, we're gonna take a look at this case. When a car is making a turn, then we can find out the force, the centrifugal force on it, which is the static friction force, right? In this question, we're gonna take a look at the centrifugal force on the car when it's making a turn. And as we discussed earlier, when the car is making a turn, okay, the centrifugal force is actually the static friction force from the ground, from the road on the car. So that's the static friction force. So in this case, how do I set up this question? So I have like a 1,500 kilogram car moving on this curve, and the radius of the curve is given 35 meters. The coefficient of the static friction between the tires and the dry pavement is 0.5. So that's the mu s. We want to find the maximum speed the car can have. So first of all, I know in this case, static friction force is the centrifugal force. So I can set up this, right? Now I do have an equation for centrifugal force. Centrifugal force, the value of centrifugal force is always going to be this, okay? So these two numbers, if I know this number and this number, they must be equal always in this case, because the static friction is the centrifugal force. Then you see, how do I find the maximum value of this velocity, the speed the car can have, and still make the turn successfully? Because this static friction force can vary from 0 to the maximum, right? So it can vary from the 0 to the maximum. So for any certain speed, right? You make this turn, you drive this car, make this turn. You need a certain value between these two numbers, so the road is always going to provide that force to you, right? But the maximum value, maximum static friction force the road can provide, it's going to be a fixed number. It's going to be constant. So you cannot ask for any force larger than this, right? If you ask the road to provide you any force larger than that, the road cannot do that. Then you're not going to be able to make this turn successfully. Okay, the car may start skidding. Okay, so then you see that when does the maximum speed occur? Right, the maximum speed occurs when the static friction force has reached the maximum. Right. So in this case, because the mass doesn't change, the R doesn't change, so the V is just going to be related to this static friction force. And static friction force has a maximum, so that is the maximum speed you can have, okay? And then still make this turn successfully. If you drive the car with any speed larger than that, the road is not going to provide the centrifugal force you need, okay? And then this maximum static friction force, we do have a theory for that. That's mu s times normal force, right? And then this is the equation. Now you see, I want to solve for the maximum speed, right? That's what I want to do. Mu s, the problem gives us, right? Mu s is 0.5 in this problem. And the radius of the curve, well, you may not notice where the center is, right, when you drive. But when this road, if this road is built as a curve, so there is a center and there is a radius, and the radius is 35 meters in this case. And then the only thing you need is going to be the normal force in this case. And the normal force, when the car is moving on the road and the road is flat, horizontal, totally flat, that's going to just be equal to gravity, right? So if you look at this image on this slide, so the gravity is down, normal force is up, and then they're going to cancel in this direction. So in this case, normal force is the gravity of the car. But this is not always true, as I said, right? I warned you many times. This is only true when something is on a flat surface, and then there's only two forces in this y direction, normal force and gravity, and they cancel out, right? So don't remember this, okay? A lot of people, when they see normal force in a problem, oh, it equals gravity. Not always. You should be careful. Not because like we use the normal force equals gravity in a lot of problems, so that becomes a law. That becomes a conclusion I should remember for every type of question I solve, right? That's not a law. Newton's laws are laws of motion. So you can always use Newton's laws if you want to study the motion of any object. So okay, so now you see that you can plug everything into this equation you just found, and then rearrange this equation, you will be able to find the maximum speed the car can have and still make the turn successfully. Okay, now you can pause the video and then finish the algebra. Okay, what do you get? You just get mu s mg equals m v max squared over r, right? You rearrange this equation, the mass and mass can cancel, so you actually get this. Mu s gr. Now I can plug numbers in. I usually plug numbers in at the end. I don't carry the numbers when I rearrange the equation. I know a lot of people like doing that, but that's how I would solve a problem. I would keep all the symbols until I reach the final expression, okay? Because working with this symbol, writing these symbols are actually easier for me. Okay? That's how I would do the algebra. Now I can, and sometimes you see that some symbols, they may cancel out when you do the algebra. So you don't need to use all the numbers to do the algebra. And then at the end, you're going to have a bunch of numbers. Okay. So if you use symbols, that's going to actually save your time. But you do need to get used to symbols. A lot of people, they are afraid of symbols. But as I said, you definitely need to get used to symbols if you study physics. Now we can plug all the numbers in. So this is going to give you a 13.1 meters per second. Okay, so this is this question. I'm going to stop here for this video.